All right, let us come back to simple harmonic motion here. We should recall a couple of things. Recall, simple harmonic motion is anything that satisfies this relationship. The second derivative of blah is equal to the opposite of something squared times blah. Blah can be anything. Oftentimes it's position, but we're going to talk about cases where it's maybe an angle, and you'll see this pop up in circuits and other places where it's nothing related to motion at all. Now this quantity omega is the angular frequency of the oscillation. And so we find that the solution to something like this, the solution to simple harmonic motion, at least a solution, looks like this. This could just as easily be sine omega t plus phi. Cos and sine just differ by a phase angle, so that just changes what phi is. You could also write it as the sum of a cosine term and a sine term. If you do some crazy things with angle addition, you can make that work out pretty nicely. You just absorb constants into each other. Key bits, second order differential equation, so two constants. Eventually you'll do this and it'll be complex exponentials, which are awesome, but not here nor there. And the first kind of standard example of this is a mass on a spring. Mass, spring. It oscillates with some angular frequency that depends on the mass and the spring. Shocking everyone. All right. So it turns out, though, that springs are actually a super important example. So you might wonder, why springs? So it turns out that any situation looks like a mass on a spring for oscillations about an energy minimum. So, this is the picture for a spring. Here is your energy minimum. Because remember that the potential energy function for a spring looks like, not minus, sorry. Getting absorbed in minus signs. 1/2 kx squared. So this is quadratic, parabolic. Literally anything else near a minimum, such as these, will look like a quadratic if I zoom in far enough. I can't zoom any further than this, but imagine I'm zooming in, and as I zoom in, this clearly near a minimum looks quadratic. So that is the claim. So let u of x be the potential function for some system. I can write u of x as an infinite series, like so. This is the Taylor series expansion for u of x about x naught, where x naught is my local minimum. So I'm expanding it about a minimum in this infinite series, where it's just a power series. I've got the quadratic term, third order term, fourth order. There's an infinite number of these things, which you might think would complicate life, but in fact, we're going to make life easier for ourselves. We can zero a potential function wherever we want. Remember, we can set anything as our zero. So we'll set this constant term up here, a naught, to 0. Whatever. We can zero things however we like when they're potential functions. They don't really exist. And they're not like in a concrete sense. They're something we impose on reality. So we set that to 0. At a minimum, we know that the first derivative of this function should be 0. Yes, because at a minimum, tangent is flat, so slope is 0. So if I take the derivative of my function, the constant term would go away anyway, but it doesn't matter. My linear term becomes constant, my quadratic term becomes linear, my tertiary, my third order term becomes quadratic, and so on. And I'm evaluating this, it's important to note, at my minimum. Yes? So this, which was x, the general x, minus x naught, the minimum, this term goes away. And it identically goes away for every single higher order term. Which means I'm left with this one conclusion, that if the derivative is 0 at a minimum, this constant a1 must be 0 at a minimum. So this is my potential energy function near a minimum, for literally any potential function, any potential energy we got. This means that any system with a potential energy function looks like a spring near a minimum, which means it will undergo simple harmonic motion. Now, this near a minimum bit is important because what I'm saying is that near a minimum, all this higher order stuff, I don't care about. Because near a minimum, the distance away from the minimum minus the minimum, so like that the position minus the minimum's position, that distance, is small. A small quantity squared is very small. A small quantity cubed is much smaller than that. So each successive term in this function is smaller than the term before it. And so we're going to just look at the approximation as this leading order term. In the leading order term, near a minimum, will always be quadratic, which means that it's always, to leading order, going to look like a spring. So, there are many examples of this, but let's look at one, specifically the pendulum. We're going to look at two cases of the pendulum. First case is the simple pendulum. Don't worry, it's not actually that simple. In the simple pendulum, we have a mass, which we're going to treat as a point mass, attached to a string, a massless string, of length L, let's say. Right? Now, looking at this, I have a situation where I'm going to have a torque. Clearly, this thing is going to oscillate if I pull it up some small angle. I'm going to stick with small angles because we need to be near the minimum. So I would expect, my weight acting on this. This distance L is, the separation from the axis. Here is my axis up here. So I would write down Newton's second law for rotation, which says that the torque is equal to I alpha. In this case, the torque is going to be minus mg sine theta. Minus mg L sine theta. Theta is this angle that I've pulled it up. If I pull it up in angle theta, let's say that's the positive direction, this force is trying to get it to go down into the negative direction. If we look at the component of this, the perpendicular component is this mg sine theta. Trust me with the triangles. Do it out yourself to confirm, but trust but verify. And so that gets us this minus sign. Also, if you do the right-hand rule very carefully, you would see you get a minus sign there. If I have a point mass, I is just ml squared. And alpha, recall, is the second derivative of theta. So as I look at this, I'm optimistic. I see a theta double dot. I might be thinking, aha, simple harmonic motion, this is easy. Don't worry, it's not actually easy. Sine theta is not the same thing as theta. However, you will come to learn at some point that sine theta can be approximated by not approximated, it is explicitly equal to an infinite series that is odd in theta. It's an alternating series that looks like this. And so on and so forth. By the same convention that we used above, we said that we're carrying only about this leading order term. We're just getting rid of this higher order stuff. If we are near the minimum, doing this for small theta, theta is very small. Theta cubed is tiny, effectively 0. Theta to the fifth, even smaller than that. So we're going to say that sine theta is approximately theta. Which means, coming back to this, we can replace sine theta by theta. So we have mgl theta equals, technically approximately, for small theta this holds out really well, ml squared theta double dot. Remember, we're looking for something that looks like theta double dot is proportional to theta. So theta double dot, dividing both sides by ml squared, looks like minus g over L theta. Which means that g over L is omega squared. So the angular frequency for this pendulum should be root g over L. That is the simple pendulum. Don't worry, there are worse. But it's a stunning example of anything about a minimum will look like simple harmonic motion. Just may take a little massaging. This bit, the small angle approximation for theta, the small angle approximation, I should say, requires that theta be much less than 1 when measured in radians. Generally speaking, this is good up to like maybe 20 degrees. So it is a reasonably small deviation from the bottom where you will get this linear behavior. You will still get oscillation if you go above. That's what we should expect from an energy analysis. It's just not going to be simple anymore, as though this were simple. Now, in case that proved to be, you were like, oh, that's not bad. It's just a Taylor series expansion. I can do this. Let's make it worse. Let us consider the physical pendulum. So what's different? In the simple pendulum, the bob of the pendulum here is a point mass. It has no size or shape. The thread is massless. Here, the entire pendulum is massive. So let us say that the pendulum has some radius r and some length L. I could then consult from the textbook our wonderful table of centers of mass. Rotational inertia is about center of mass, and I would see that the rotational inertia about the center of mass for something like this, a solid cylinder through its center of mass spinning in the way that this is spinning. I realize I'm not going to be able to draw that meaningfully. Spinning as though you're like spinning your pencil or something, or a pen over your fingers, not spinning like a top. Looks like this. But it's not spinning about its center of mass. It's spinning about, let's say, the very top of the cylinder. That's where the axis is. So I need to use the parallel axis theorem and shift it. I'm going to shift it by L over 2. So this would give me 1/4 mr squared plus then 1/3 ml squared. Yes? The other bit that's interesting is that before, the force of gravity was acting at the bob because that was the center of mass, basically, of the system. That's where all the mass was. The center of mass of this shape is now somewhat arbitrary. It so happens that it is constrained by symmetry, in this case, to be at the center of the cylinder. But that means that this lever arm distance, which I'll say h in general, in this case it happens to be just L over 2. But that's not, as much of a given to us as it was in the case of the simple pendulum. So if I go now to write down Newton's second law again, tau equals I alpha, I would have still mg, this is going to be h sine theta, the minus sign, equals this horrifying monstrosity times theta double dot. But if we make the small angle approximation again and plug in what we know h is, we can see that this still resolves back down pretty cleanly to a manageable expression. Manageable maybe in scare quotes. Minus, all right, m's are going to cancel, so we have g L over 2 over 1/4 mr squared plus 1/3 ml squared theta double dot. If I hit that whole thing with a factor of 12, I guess, or multiple of 12, minus 6gl over 3 mr squared plus 4 ml squared theta double dot. So this, nope, hold on, that's too many theta double dots, theta. This is a theta double dot, this is the theta. I can do division, I swear. This crazy thing is my omega squared. And that is the point of this. This is why, we're coming kind of back to this idea of just oscillatory motion. Waves have come up in the past. And the reason that we keep coming back to these is because it's a very powerful descriptive tool that's a good first approach to almost any oscillating system. Anything that's acting near its minimum, this is going to describe its behavior. So, this is the basics of simple harmonic motion from last time, but the power of this is that we can take this to any system near its minimum with this justification, and then this is what it starts to look like. You have to do a little bit of trickery sometimes to get it to exactly look like this. But basically all that we're doing is trying to write down the potential energy function and solve for the linearized form of the force. If that makes sense. Right. Simple, physical. You will see examples in your book of torsion pendulums, pendulums that are spinning around an axis instead of kind of swinging back and forth. And you'll see other examples about damped motion. It's not as important to be able to do the calculations with damped motion, so there's not going to be a screencast. But you do want to look at it and try to wrap your head around the basics. Good luck.